Hello, everyone, and welcome again. This is Professor Brian Macon. I am your derivative doctor, part of the Department of Integration, and your curator of Calculus Fun. Oh, yeah, that reminds me, whenever I have a calculus class, or any math class actually, and right at the beginning of class, I usually say, "Welcome to the Math Fun Room." And most people appreciate that, so I'm the curator of Calculus Fun, and welcome to this Calculus Fun video. Again, Professor Brian Macon coming at you live, and we are going to take a look today at partial fraction decomposition. Now, typically in this kind of conversation, it is a review in the beginning of some form of doing the decomposition. So usually before you get to a calculus course, you have learned in a pre-calculus class typically how to do partial fraction decomposition. So usually in a section like this in a calculus course, part of what you are doing is shaking the rust off of that algebra topic of doing a partial fraction decomposition. So let's take, maybe the first 5 minutes of this video before we actually get into integrals, and let's just remind ourselves about what partial fraction decomposition entails, and how would we go through that process, right? So first of all, I will pose the problem as an integral. So this board seems to hate me and always jumps to some other page when I first start writing. So, all right, so we have the integral of, let's say, 1 over x squared minus 1. All right, now if we stop for a moment and we talk about strategies of integrals, this integral is not a known form. Now, if I had the integral of 1 over x squared plus 1, just as a reminder, I'm going to come back and erase this in a second. But the integral of 1 over x squared plus 1 is inverse tangent of x plus c. Ran out of room there, right? So that's a known integral, right? And that's not what we have in this case. If I had something like x over x squared plus 1, then this would be a u sub problem. I would let u equal x squared plus 1, and I'd get, basically 1 over u du, which is ln in that case. Let's see, if I had the integral of 1 over the square root of x squared plus 1, this would be a trig substitution problem like we talked about in the last video, right? And I would set up my triangle. I would look at the square root of x plus 1 on the hypotenuse, and then let's say x and 1 here. So any of those three forms we have already discussed. Now in this section, or this problem in particular, we're looking at a form of an integral, 1 over x squared minus 1 being our integrand, where we don't match either of those forms that we just discussed. So we don't know the technique in which to do this. And the process that we're going to go through with the partial fraction decomposition is we'll first decompose the fraction, and then we will come back and evaluate the integral. All right, so without jumping into all the rules of decomposition, let's take a look at this particular example. And let's look at, we want to decompose this fraction. So in other words, if I factor this fraction, so whenever I am looking at a fraction like, let me come back over here for a second. Let's say I'm adding the fraction 1 half and 1/8, right? So usually what we do in an arithmetic class of this nature is we get a common denominator, right? And the way that we get a common denominator is we find the least common multiple of the two fractions that we have there. And we could multiply 2 and 8 and get 16, and that is a common denominator, but it's not the least common denominator. It's not the least common multiple between 2 and 8. And a lot of times when you first look at, arithmetic conversation here, usually beginning math course, what you do is you look at the prime factorizations of each of these denominators, right? So I might look at 8 as this was 2 to the first, right? And then I would factor 8, 2 times 2 times 2, which is 2 cubed. So I would have to look at the common factors there, and we would say 2 cubed is the common factor, right? All right, so I don't want to get too far down that rabbit hole there, but what we're going to do in essence, so if we take 1/8 and we ask ourselves, what two fractions do I add to get 1/2? Excuse me, what two fractions do I add to get 1/8? Here would be one possible solution. So what we basically do is we take the factors in this denominator and we break them up. We break them up into 2 cubed and 2 to the first. Now, technically, what I actually should do is I would say, well, I could have a fraction with 2 to the first in the denominator. I could have a fraction with 2 squared in the denominator. And I could have a fraction with 2 cubed in the denominator. So technically, I could add 3 fractions. One that has a factor of 2, one that has a factor of 4, and one that has a factor of 8. So anyway, so when I come back to the decomposition rule, what I'm going to do here is I'm going to assume that there could have been a fraction with x minus 1 in the denominator, and there could have been a fraction with x plus 1 in the denominator. So we're going to assume this is the decomposed form, and what we're going to do is we're going to basically find the numerators that would make this decomposed form true. So we're going to assume a constant in the numerator. And when we come back in a couple minutes and we talk about the rules of the decompositions, what we're going to basically say is we want a proper fraction in our decomposed form. So if the denominator is linear, we're going to assume the numerator is 1 degree less. Right? If the denominator is quadratic and I can't factor it, right? So if the denominator is an irreducible quadratic, I assume the numerator is actually linear. So I assume a proper fraction. Again, we'll talk about that in more detail in a second. So here's my assumed form of the decomposition. And we know that this is a correct assumption, similar to like what we talked about over here. We have to look at all possible factors of the denominator as having their own fraction. All right. Typically, the way that I like to do this personally is I think of, if I get a common denominator over here, it should equal this fraction, right? So I would have 1 over x minus 1 times x plus 1. And if I get a common denominator on the right-hand side, like what's my common denominator? Well, it's, x minus 1 times x plus 1. That's my common denominator, right? So what do I have to do to this fraction to get the common denominator? Well, in the denominator, I have to multiply by x plus 1. So in the numerator, I'm going to multiply by x plus 1. And then in this fraction, what is its denominator missing? Right? It's missing the x minus 1 factor. So I'm going to multiply down here by x minus 1. I'm going to multiply up here by x minus 1. So if I get a common denominator, right, that's what the right-hand side looks like. Now, let me erase that squiggly I just drew. Right? So now to take this to the next step, right, if these two things are to be equal, now that the denominators are equal, then the numerators have to be equal. So the numerator of the left-hand side has to equal the numerator of the right-hand side. All right, so if I'm at this point, there's a couple shortcuts that I could take here. Right? First, I want to show you kind of the long correct process, and then we'll come back and we'll talk about a shortcut that we could take at this point. So if I take the longer process, right, I'm gonna multiply everything out here, and I'm gonna get ax plus a and then plus bx minus b, and all of that is supposed to equal 1. And then if I combine the like terms, I have ax plus bx. So when I combine the like terms, I add the coefficients, and then I'm going to add the constants together. So I'm just going to write it that way. Now, keep in mind, these two things are supposed to be equal to each other. So on the right-hand side, I have a linear expression. Right? I have, something x plus a constant. So over here, my constant is 1. So I know that this constant a minus b has to equal 1. And then this constant of the coefficient of x has to equal the coefficient of x over here, which I don't have in x. So that means that the coefficient is 0. Right? So I know that if this fraction decomposed form is true, when I get common denominators, I know the numerators have to be true. When I set the numerators equal to each other, then the x coefficient has to equal the x coefficient here, and the constant has to equal the constant here. And this produces a system of equations. Right? So I'm just going to kind of highlight, right, here's my constant, and that has to equal 1. Right? And then here's my constant, a plus b, my coefficient of x, and that has to equal 0. Right? So I'm going to write that system over here. So I have a plus b has to equal 0, and then I have a minus b has to equal 1. So I have to solve this system. Here's a system that we have to solve. And when we solve that system, that finds the a and the b that live in the numerator of my decomposed form. Right? So whatever value I get out of a in the system, that's the value of a up here, and whatever value of b I get in the system, that's the value of b that I get here. Now at this point, we're still doing algebra, right? So we're solving this system, and however I solve the system doesn't really matter, right? So usually in an algebra course, you learn about substitution or you learn about elimination, which I call the addition method. So that's actually the approach I'm going to take here. I'm going to add these two equations together because when I do that, I notice that the b's are going to cancel. So the b's cancel, and I get 2a equals 1. Or a is 1/2, right? And then if I come back, let's say, and plug into this first equation, right? I know that a plus b has to equal 0. So a has to equal the opposite of b. Or I guess what I'm looking for is b, right? I already have a. What I'm solving for is b. Let me erase that, right? I'm solving for b. b is the opposite of a, so I have the negative of 1/2. So there's our a and our b of our decomposed form. Now, I'm running out of digital paper here, so let me scroll back up again. So a is the numerator of the x minus 1 factor. b is the numerator of the x plus 1 factor. So a is the numerator of the x minus 1 factor. So I have my decomposed form here. So I have the a is the numerator of the x minus 1 factor. Oops, sorry. And the a was positive 1/2. 1/2 over x minus 1. And then b was the numerator of the x plus 1 factor. Did I say that right? I apologize, guys. Let me scroll back up real quick and just make sure I'm writing that down correctly. So the denominator of the x minus 1 was the a. All right, so I had that right. So the denominator of the x minus 1 is the a. So in other words, here's what we're looking at. We're saying the fraction 1 over x squared minus 1 equals this guy. Right? Now, in reality, what we're doing is we're integrating. So we're saying the integral of this guy is really equal to the integral of all of this stuff. Right? To keep in mind, when I integrate these fractions here, I'm going to split it up. I'm going to split those two integrals into their own pieces. So I'm going to have the integral of 1/2 over x minus 1 dx, and then plus, the integral of minus 1/2 over x plus 1 dx. So let me stop here for a second, right, and say this is the idea. This is the concept behind partial fraction decomposition when we apply it to an integration. So we're gonna have an integral, right, and the integrand we're not going to be able to do u sub. We're not going to be able to identify it as a known integral. There's no radical in it, so it's probably not going to be trig sub. So partial fractions is a possible process by which we use to evaluate that integral. So the partial fractions involves the algebraic process of breaking the fraction up into simpler forms, if you will, and then we integrate each of those simpler forms. So just to finish this problem off here, I'm going to go ahead and pull the 1/2 in front of the integral, and I have 1 over x minus 1. And then I'm going to go ahead and pull the negative 1/2 in front of that integral. And I have 1 over x plus 1. Right? And then, keep in mind here, 1 over x is the ln of the x. Right? And then I have the minus 1/2 ln of x plus 1. Okay? And, I guess plus c. And there is our final answer. Okay? So that's an example of what partial fractions is all about. Partial fractions is a way for us to deal with a rational expression, really. We break the rational into smaller pieces, and then we evaluate each of those smaller pieces. And I just want to come back for a second and let's look at each of these integrals here. Technically I'm doing the u substitution with this. I'm technically doing the u substitution with this, right? I mean, just to scribble that out for you real quick, if I was looking at the integral of 1 over x plus 1, right, I mean, technically I'm letting u equal x plus 1 so that I'm going to get a 1 over u form, and then the du is 1 times dx, right? So the dx equals du, and so there's my, ln of u form, which in this case, my u was x plus 1, all right? So, by all means, feel free to do the u sub on that, okay? But basically 1 over x is the ln of x is an integral. I do want to caution you on that. Let me talking about that. Technically, if I have like 1 over, let's call it ax plus b that I'm integrating, and I'm going to do a u sub for the denominator, and I'm going to get 1 over u. And then I'm going to have the du being the coefficient of the x dx. So the dx is 1 over a du. That's my dx term. Right? So I really have like 1 over a du. That's what my dx is equal to. So I want to be a little careful. What I just said was if I integrate 1 over a linear, it's the ln of the denominator, right? That's not technically true. So I'm going to have 1 over a come out of that integral, and then I'm going to have the ln of u. So technically, if the denominator is linear and the numerator is constant, then I have 1 over the x's coefficient that sits in front. All right, I just want to caution us there based on what I said a second ago. All right, so anytime you're doing an integral that involves partial fraction decomposition, the first step actually is some algebra. We're going to assume a decomposed form, and we're going to follow that decomposed form to find the numerators of each decomposed form, and then we're going to do the integral finally. So in a pre-calculus course, you learn about the couple different rules of decomposition. So let's take a couple minutes to just illustrate the rules of the decompositions here. All right, so let's take a look at the rules for decomposition. Now, usually in a standard calculus book, you have these rules presented to you in a very generic form. I'm just going to illustrate examples, all right, just to save some time here. So the first example that we saw is what we're going to talk about here. So, for example, we had 1 over, x squared minus 1. So the first thing we're going to always do, kind of step 1, right, we're going to, can we factor, right? We're going to always factor the terms in the denominator to their simplest forms. Right? So we wrote this as 1 over x minus 1 times x plus 1. Right? We had the difference of squares. Right? And then the next rule, let's say, is once we're factored, any linear denominator gets a constant numerator. So we're gonna break all linear factors to have their own fraction. And anytime it's linear, we get a constant numerator. Right? So again, the illustration of our example from the first problem that we just did, we're going to write this as, x minus 1, we get a constant in the numerator, and then x plus 1 constant in the denominator. So that would be the proper decomposed form for when I have linear factors in the denominator, right? The denumerator. I had a student in a class one time. I loved it. I use this in my algebra classes now, but when we were doing the quadratic formula, the term under the radical is called the discriminant, and it determines the nature of your solution. solutions, right? So if the discriminant under the radical is negative, you get complex or imaginary solutions out of the quadratic equation. If the discriminant under the radical is positive, you get two real solutions, so on and so forth, right? So I had a student that couldn't remember the term discriminant, but because it determined the nature of the solutions, they called it the determinator. So it was pretty funny. I had another student, we had a good laugh about it, and I said, hey, look, I don't care what you call it, as long as you remember what it does. So we had a student draw a cartoon, really creative student that semester, he's very good artistically. So I drew a picture of the Determinator, of the Terminator, right? Arnold Schwarzenegger is the Terminator. And then he had like a math problem he was solving, and called it the Determinator. Pretty funny. All right, anyway, so this is not the denumerator, this is the denominator that we're looking at. So if the denominator has linear factors, each of those linear factors gets its own fraction with a constant numerator. Oh, something else I noticed students ask in class. Does it matter if the x minus 1 denominator has a in the top or b in the top, right? Does it matter if the x plus 1 denominator has a in the top or b in the top? And the answer to that question is no, it doesn't matter, right? Whatever letter I put in the numerator of x minus 1, if its value is 1/2, that's what we'll find, right? So if I called this numerator here L, and I called this numerator here W, L is going to be 1/2, right? W is going to be negative 1/2. So the letters we use there don't really matter. Just keep that in mind. Right? So if I wrote b over x minus 1 and you put a over x minus 1, it doesn't matter. Our numerators will turn out to be the same. Okay, so the second example I want to look at is where we might have a repeated linear factor. So let's say we had 1 over x minus 1, and let's say we had x plus 1 quantity squared. So the rule in this case is for the repeated linear factor, we have to look at all possible powers, right? All possible factors of that repeated term. So the repeated linear factor, each fraction must have all possible powers, right? Must have all possible, and I'm going to call that factors, right? All possible factors, right? All possible powers of that repeated term. So I'm just going to put 1 in the numerator there. So if I break this up, I'm going to have x minus 1 as its own fraction, and then I'm going to have x plus 1 squared, and then x plus 1 to the first. Right? So, back on our first page, if I scroll back up here for a second, I apologize for jumping back and forth here, right? But if I scroll back up to our first page when we were using those fractions of 1/2, right, like we had right here, right? This is technically a repeated factor. 2 cubed is 2 times 2 times 2, right? So in theory, the repeated linear factor, I could have had a 1/2, I could have had a 1/4, I could have had a 1/8, right? So for this illustration, we only had a 2 to the first and a 2 cubed. As it turns out, the 2 squared had a numerator of 0 because it was missing. But anytime we have a repeated factor, we have to assume all possible exponents of that factor. So when we're writing these rules here, we have to make that same assumption. Okay? So we have to look at all possible factors of this repeated linear term. Now, anytime I have a linear term, we have to have a constant numerator. So let's say I call this A, let's say I call that B, let's say I call that C. Now, a lot of students will say, no, wait a second, this factor here is quadratic. It's not linear. So if this is quadratic, why aren't I writing like bx plus c here, right? The 1 degree less proper fraction. And it's because this, even though this is quadratic, I agree with you, it's really linear. It's a repeated linear term, and that's how we're going to treat it. Okay. All right, so that's kind of the second rule. What if I have a repeated linear term? The third rule would be, what if I have a quadratic that's irreducible? So in this example, let's say I have 1 over x times, x squared plus 3. Right? So this doesn't factor. Right? So if we have what we call an irreducible quadratic factor, then we just write that quadratic factor, right? Then it gets a fraction. It gets its own fraction with a linear numerator. All right, so for this example, notice the way that I wrote this is I have a linear term in the denominator, so that linear term gets its own fraction, and then I have the quadratic term that doesn't factor, and it gets its own fraction. So this first fraction is linear in the denominator, so it gets a numerator that's 1 degree less, right? An x to the 0 numerator, which is a constant. And then this is a quadratic that doesn't factor, so it gets a 1 degree less numerator as its assumed form. So we get a bx plus c in the numerator. All right, now again, I mentioned kind of at the beginning of the video, we're going to always assume that these fractions are proper, right? So in other words, they're less than 1, quote unquote less than 1, right? 1/2 is, or let me say 2/3 is proper, 3/2 is not proper, right? So these are proper fractions, right? And so the numerator's degree has to be smaller. Now we're always going to assume kind of worst case scenario, right? I mean, I could have put only a constant up here. That's a smaller degree than the denominator, but we could be missing the linear term, right? So we're going to assume it's 1 degree less. Right, and then usually the next rule that you see in a pre-calculus course is, well, what if the quadratic term is repeated? Right, so let's say we have x squared plus 3 to the 3rd power. Right, so same thing as the linears, right? So a repeated quadratic must consider all possible factors. Must consider. I can't write today. All right, must consider all possible factors. So in this illustration, right, I have x squared plus 3 cubed. So I have to look at x squared plus 3 cubed, and then I have to look at x squared plus 3 squared, and then I have to look at x squared plus 3 to the 1st power. All right, so just like we talked about earlier with the repeated linear factors, even though this is technically, a 3rd power to the 2nd power, it's a 6th power, it's still quadratic. It's just a repeated quadratic, right? So because this is a squared in the numerator, denominator, that's an ugly 2. Let me fix that, right? So because this is a square, then I'm going to assume a linear numerator. So I'm going to say, ax plus b. And then this would get like a cx plus d. And then this would get, let's say, like a ex plus f. So look, I'm going to stop there. I mean, this is the extent of what you would basically see. Right? We're going to always have the denominator factored as much as possible. And we're going to follow, kind of one of these 4 rules, these 4 examples. Now, if we scroll back up, I'm not going to, actually, let me scroll back up because I want to be able to point this out to you. If we scroll back up for a moment, when we solved this decomposition here, we ended up with a system of equations. So we had our assumed decomposed form, and we got a common denominator. Let me scroll up a little bit more, right? So we had our assumed decomposed form here. We got a common denominator. We set the numerators equal to each other. And then when we gathered like terms, we basically created a system of equations. We said the coefficient of the x term had to equal the coefficient of the x term here, and then the constant has to equal the constant here. So that creates a system of equations. We had two unknowns, a and b, and 2 equations. So in all of these other examples, if I follow this lengthy process, I'm going to get the same type of workflow. Right? So in other words, if we stop and look at this guy right here, I have 3 unknowns in my numerator. So when I set up that system, I'm going to have 3 variables, if you will, 3 unknowns, and I'm going to need 3 equations. So I'm solving a system of equations. It's a 3 by 3. Right? This can get a little hairy, right? Can get a little lengthy. If you look at this example here, the one that I gave you, same type of idea, right? I'm going to have A, B, and C as my unknowns, so I have 3 three unknown constants, I'm going to have three equations to solve that system. Here's our last example that we looked at. This one's really ugly, right? Because there's six unknown constants, A, B, C, D, E, F. So I'd have to have six equations to solve that system, and it just gets really unmanageable. Right, so usually, within the safe confines of a calculus course, you don't usually see a problem that is that crazy and that lengthy. That's just too much work. So conceptually, we're looking at decomposing a fraction. And that's really what we want to focus on. We don't want to get too bogged down into the details of the algebra. Right? Now, I do want to come back and look at our original examples and tell you the shortcut that I had mentioned to you sooner. Now, personally, I prefer to do the system of equations. I think it's so much easier to do the system of equations. All right? But if we were going to do the shortcut in that first problem, let's talk about the shortcut. Right, so let's come back to the example, and then let's talk about the shortcut. Back to the example, and let's talk about the shortcut. Okay, so we ended up with, what did we have? We had 1 equals a times x plus 1. And b times x minus 1. So when we set the numerators equal to each other, we ended up at this step. So one thing we can do to kind of cheat is we can say, how do we zero out a term? All right, so I'm going to put over here, the note is we're going to zero each term. Right, that's really what we're going to do. So in other words, if I plug -1 into this factor, it makes it 0. And 0 times a gets rid of the a. So if I plug -1 into this equation that we have right here, I'm going to have on the left-hand side, I'm going to have 1. And on the right-hand side, I'm going to have 0a. And then I'm going to have b times, that would be -2 if I plug that in. So I get 1 equals -2b, and b is -1/2. So it's an actually nice little shortcut. Now this shortcut doesn't always work, but sometimes it does. So, what I say to you is try the shortcut. Right? See if the shortcut finds a value of one of the constants for you. If it does, sweet. If it doesn't, okay, we'll go back to the system approach. So the system approach is more mathematically correct, but this is a nice shortcut, and when it works, use it. So if I'm zeroing the other term, let's see, x equals 1 would zero this term, and it would make the b go away. So if I say, what if x is equal to 1? Then we're going to zero the b term. So I plug x equals 1 over here, and it's just 1. There's no x over there to plug into, and I get a times 2. So a is 1/2. Okay. All right. So there's a nice little shortcut. Let's do one other example where we would have a shortcut that might work. Or actually, let's do this. I think you get the general idea to the shortcut. Let's talk about the use of technology. It depends on the instructor that you have. Not sure what kind of technology you would be allowed to use. But this example that we just looked at here, let's scroll all the way back to the top again. And let's talk about the form that we had set up, right? So what was our system that we had? Oops. This thing's really lagging. Here's my system that I have right here. Right? So I have a plus b equal to 0, a minus b equals 1. So let me come back down here. So using technology, right? Let's say that we're going to use technology for this guy, right? So let's talk about using technology for the system. Okay, again, this kind of falls back to a pre-calculus course, right? So we had a plus b equaling 0, and we had a minus b equaling 1. All right, so I want to kind of step to the side here for a second and talk about how, like, if we had in a pre-calculus course, if we had the system x plus y equals 0 and x minus y equals 1, we would put that into a matrix form. So the terminology that we used in that class is we wrote the augmented matrix. So what we would basically do is take the coefficients. The first equation has a coefficient of 1, 1, and that equals 0. And the second equation has coefficients of 1, -1, and that equals 1. So we would use, brackets as, the notation for the matrix, and then some books put a little dotted line here to just remind you that there's the equal sign. Now that's not really a part of the matrix, but that's sometimes visually how we can separate those ideas, right? And then we could solve this system, and technically there's a couple ways to do this. One way would be we could use what's called Cramer's rule. Another way we could use the inverse matrix technique. Another way is we could use Gaussian elimination to reduce this matrix into what we call row echelon form or reduced row echelon form. Now, over here, I'm going to really do the exact same matrix, right? Instead of x's and y's, I have a's and b's. So this in matrix form really is that guy right there. I'm going to pluck the coefficients off. So my unknowns in this system over here are x's and y's. My unknowns here are a's and b's. All right, so let's suppose I have access to a graphing calculator, and the graphing calculator I have here is a TI-84, some version of a TI-84, right? So if I'm going to do this system and technology, then one of the things I'm going to do is use the matrix. Right? So if you look above the inverse key, it says matrix. So I'm going to do second inverse, and it's going to take me to the matrix. And the first thing I'm going to want to do is choose edit. And I can pick any of these matrices I want. I'm going to pull out the first one. And it wants me to first specify the size. So I have 2 rows by 3 columns. And there's the size of my matrix. And I'm going to type in the coefficients that we had. So we had 1, and then we had 1 and 0, and then we had 1, and then we had -1 and 1. Oops, sorry, that would be 1. Okay, let me just make sure I did that right. We had 1, 1, 0, 1, -1, 1. All right, so here's my matrix, and then I'm going to go back to the home screen. I'm going to do second mode, quits me to the home screen, and then I'm going to call out. I'm going to go back to matrix. Where's that second matrix? And in this case, I want to do some math with a matrix. So a couple different ways to do this, right? But the way I prefer to do it is putting the matrix in what we call reduced row echelon form. So I'm going to call out a reduced row echelon form, and I'm going to tell it I want to perform this function on matrix A, the one we just entered. So I have to go back to matrix, second inverse key, and I have to call out the matrix whose name is A. And then when I hit enter, it's going to put the matrix into reduced row echelon form. And what I can do on this calculator is I can do math and then turn it to a fraction, and it'll give me fractions for those values, right? But that's basically the matrix technique, right? Matrix solution for that system. So you can see here in this case, what this is saying is A equals 1/2, B equals -1/2, right? Remember, if I pull this out of this matrix, this is 1 times A plus 0 times B equals 1/2. This is 0 times A plus 1 times B equals -1/2. So A is half, B is -1/2. So if I'm allowed to use technology, this is a nice way in a TI-84 to solve that system. There's other types of calculators out there, right? There's Casio, there's Hewlett-Packard, there's even TI Inspire. So there's a couple other, I want to say it's the same concept, right? But there's different calculators that are out there. So I don't have those emulators on my computer. Feel free to use YouTube, right? And search on YouTube for solving a system with, HP calculator, right? Whichever one that you might have, right? So a nice way to kind of check our work there. All right, now this video is running a little longer than I wanted to. I usually like to keep videos around 30 minutes, and we're approaching almost 40. But I do want to do one more example with you here, and then we will call it quits. All right, so I'm just going to make this up on the fly here. This could get a little bit dangerous, all right? So let's see if this works out nicely. So let's say that I have the integral of 2x plus 1 over, let's say, x squared times x minus 3. So this is the integral that I'm trying to evaluate. And quickly, if I talk about does u sub work here, u sub isn't going to work here, right? Because the denominator is cubic and the numerator is linear. So if I let u equal the denominator, I'm not going to be able to take care of the numerator, which is linear. All right, so remember the first thing we have to do is the decomposition. And usually with these problems, that's where you spend the most time, is in the decomposition. So we're going to take a little bit of time here and do the decomposition first. Right, so I'm going to first of all just talk about the decomposed form. So again, let's set the form up for the decomposition. So, here, this is a little tricky sometimes. That's why I picked this example. This technically is the linear factor x minus 0 squared. So it's a repeated linear factor. So I have to have all possible powers of that repeated linear factor. So again, x squared, it's a little tricky. It is a linear factor of x minus 0 squared, so it's repeated. So this is linear. I get constant numerator. This is technically linear, right? Repeated linear gets a constant numerator, and then this is linear, and it gets a constant numerator as well. So if I get a common denominator right hand side and set these equal to each other, and I don't want to go through the process of actually getting the common denominator on the right hand side, let's just talk our way through it. So when I look at this first fraction, here's my common denominator over here, right? So I'm going to ask myself, what does this denominator need to be multiplied by to become this term? So it's missing one of the x's, so I'm going to multiply this by x, and it's missing the x minus 3. So the numerator has to be multiplied by x and x minus 3. So that would be the numerator that we would get from that first fraction. And then ditto on the second fraction that we have here, what is it missing in the denominator? Well, it's missing the x minus 3 term. So its numerator and its denominator would be multiplied by x minus 3. And then this last fraction, right, obviously it's missing the x squared term in the denominator. So its numerator and denominator gets multiplied by that term. And there we are at that point. Now, I could stop here and I could do the shortcut, and I'm going to do that. Right? Let's see if the shortcut works on this problem, because it's a little quicker. It's a little more efficient. So remember, I'm going to zero out terms. So if I plug x equals 0 in here, it's going to get rid of the a, and coincidentally, if I plug x equals 0 in, I'm going to get rid of the c. So I'll be able to find the b term when I do that. So I'm going to say, well, what happens if x is equal to 0? Well, on the left-hand side of x is equal to 0, I end up with 1. And on the right-hand side of x is equal to 0, I'm going to get negative 3b. Right? So that tells me b is negative 1/3. So we found b pretty quickly, actually. That was really nice. All right, now the next term I could zero is x equals 3. So x equals 3 would get rid of the a and b factors. Right? So if I plug x equals 3 into the left-hand side of the equation, I'm going to get 6 plus 1, which is 7. And if I plug 3 into here, I get 0. Plug 3 into here, I get 0. Plug 3 in here, I get 9c. So c is 7/9. So pretty quickly, we have found b and c. Now, how do I find a? So here's where the shortcut begins to fail. In this example, I can't find a. Right? If I get rid of the b, I'm plugging in x equals 3, but that also gets rid of the a. And if I'm getting rid of the c, I plug in x equals 0, but that also gets rid of the a. So what do I do in that case? Well, actually what I'm going to do is plug in a different x. So let's say I plug in x equals 1. So if I plug in x equals 1, on the left-hand side I get 2 plus 1, which is 3. And if I plug in x equals 1 over here, I'm going to get, let's see, 1 times negative 2. So I get negative 2a. And if I plug 1 in here, I get negative 2b. I guess I just wrote that as a minus, right? And if I plug 1 in here, I get plus c. And if you think about this for a second, I know what b is. We just found that. I know what c is. We just found that. So I can plug those in and then find a. So I would have negative 2a minus 2 times, we said b was negative 1/3. And then c is 7/9. All right, and then we could solve this for a. right? So let's see. I have negative times negative is a positive. So this is really being added on this side. I'm going to subtract it over to this side. And then this is positive 7/9, so I'm going to subtract it to the other side. Right? And then that's going to equal negative 2a. So let's go ahead then and get a common denominator here. Common denominator is 9. So I have to multiply this by 9 over 9, so I get 27. I have to multiply this by 3, so I get 6 in that numerator. And this already has its common denominator. All right, that's negative 2a. So what do I get here? 27 minus 6 minus 7. See, that's 27 minus 13, which is 14. So I'm getting, let's say I'm getting 14 over 9 equals negative 2a. And then I'm going to multiply both sides by negative 1/2 to solve for a. So if I divide negative 2 over here, this becomes a 7. So I get negative 7/9 equals a. So there's my 3 constants for each of my numerators. Now I'm old and forgetful, so I'm forgetting what I had where. So where was my a? My a was over the x. So my a is negative 7/9 over the x. And then the b was over the x squared term. So what did we say our b was up there? Our b was negative 1/3. Our b was negative 1/3. And then our c was positive 7/9, and that was over x minus 3. Right? So our original integral now equals the integral of all of that stuff. So we're finally back to the calculus. Right? So we just did quite a bit of work to decompose our original fraction. We have decomposed into this form, and then now I'm going to evaluate each integral separately, right? So the first integral is going to be negative 7/9, integral of 1 over x dx. And then I'm going to have 1/3 the integral. All right, let me stop for a second. This is 1 over x squared, which is x to the negative 2. Right? And then I'm going to have plus 7/9 the integral of 1 over x minus 3. Now, the way I paused for a moment here, I've seen in my classes a lot of times, students will say, well, 1 over x squared is ln of x squared. And please don't do that, right? Remember, 1 over a linear, right? A constant over a linear is logarithmic as an antiderivative. But any other denominator, right, doesn't give me logarithmic. So I just want to remember, 1 over x squared, I have to technically do the power rule here. So I'm going to have negative 7/9 ln of x. I'm going to have plus 1/3. So let's see, add 1 to the power, divide by the new power, and then 7/9 ln of x minus 3, and then all one big constant, right? So I guess final answer, I could say negative 7/9 ln of x. And then this would be minus 1 over 3x, and then plus 7/9 ln of x minus 3. Oops, ln of x minus 3. All right, so look, I wanted to do one more example for you to just show you the shortcut one more time, how it can work in most scenarios. And then just a little bit of a lengthier antiderivative from our first example. And so without spending too much time on more of the algebra of the partial fractions, this really is a good sample of examples and conversation in that technique of partial fractions. All right, I look forward to seeing you in the next video where we will talk about approximating integration.